I'm going to go over the answers to the free response questions on the Unit 6 practice test. So we're just going to do 26 through 30 here. Now on 26 it says explain why the feels cold when we put the ammonium chloride in water. Now this is what we passed around in class. Ammonium chloride, ammonium nitrate, both of those would do it. And it felt cold. Now the reason it felt cold is that the heat is going from your hand to the baggie. So this is a very bad picture of a baggie. But the heat is going from your hand to the baggie. So the baggie, the chemicals in the baggie are gaining energy. And so since they're gaining energy, that is endothermic. So the reaction feels cold because the reaction is absorbing energy from the surroundings. In this case, your hand is part of the surroundings. 27. What is the final temperature when 32 grams piece of diamond at 33.5 degrees is heated with 360 joules of energy? Okay, when we're doing temperature changes, we're heating up the stuff, then it's the Q equals mc delta T, that reaction, so that's our equation. So let's go back and get our numbers. So Q, it gives in the problem that it's 360 joules. The mass, it says it's a 32 gram piece of diamond. And then this is given, and hence it has to be given to you, the C for this, so 0.509. Notice it's joules per gram degree. So we've been doing heats in kilojoules. In this case, we need it in joules because it has to match the units here in our C. And then the temperature, which is always final minus initial. So we're going to heat it up. So our final is what we're looking for minus the temperature we're given, 33.5. So now we just substitute into our equation. So Q equals mc delta T. We want our delta T, so we can go back and say, well then delta T, solve for that, equals Q over mc, like we have here. I kind of covered it up. So we substitute in our numbers, and then we find out that our temperature change is 22.1 degrees. That's not our final answer, because our answer is what's the final temperature. So we have to say, what did we have to start with in order to end up with 22.1 degree change? And so the answer is 55.6 degrees Celsius. On to 28. What's the value of the delta H of vaporization of methanol if 27,050 joules is released when 24.5 grams of methanol condenses? Okay, so one little thing is we're talking about heat of vaporization, but we're going to get that from condensation. So whatever the delta H is, okay, that would be the delta H of condensation, which would be the opposite sign of the delta H of vaporization. So when we're done, we have to change the sign. This uses our equation here, and this is the one where it says Q, heat, is equal to the number of moles times the delta H of the reaction. Or we can turn that around and say delta H equals Q over N. So the delta H is the heat over the moles. So the heat is given in joules, and usually delta H is kilojoules per mole. So we're going to move the decimal point, and we're going to say our energy released negative 27.05 kilojoules. And we need the moles, but we're given grams, 24.5 grams. So we use the molar mass of our methanol and just change that into moles. So we know the Q, we know the energy, we know the moles, so we just divide them, and then we get our answer, negative 35.4 kilojoules per mole. That would be the delta H of condensation. So our final answer is right here. Change the sign, so that's the delta H of vaporization. Number 29. It says here we have a block of ice at negative 5 degrees, and it's heated to water at 25. So the first thing is to look at this picture, kind of decide on that. So we're starting way down here in the ice, below zero, and we're going to end up at 25 degrees. So we're going to have to warm up the ice to zero, then we're going to melt the ice, and the third thing then is to warm up the water that results. So we actually have three different portions, three different calculations we're going to have to do. So part B, describe what's going on. So in segment 1, okay, the sample stays as a solid, but the temperature is increasing from negative 5 to 0. So it's a 5-degree change. In segment 2, we are melting that water, that ice, and then but it stays at 0. And then in segment 3, now we have liquid, and we're just warming the liquid up from 0 to 25 degrees. Now part C, if we're going to do 3 separate calculations, anytime we do these little slanty parts where we have a temperature change, then the equation is Q equals mc delta T. And for the flat portions, you can see we're going to do an equation here. It's just moles times the delta H of fusion or delta H of vaporization, in this case fusion. So a little bit easier just to follow along the calculations. So Q equals mc delta T. Okay, mass is 40 grams. Okay, here we have to go back and say, well, what is C for ice? Because C for ice is different than C for liquid or C for steam. So, the information will be given to you, but be sure to use the right number. And the delta T, we're saying, is going from 0 to 5 degrees, so it's a 5-degree change. And then this is in joules. Okay, we're going to change it to kilojoules so that all 3 numbers can be added together. So we're starting off here for part 1, it's just 0.42 kilojoules of energy, Q equals mc delta T. For the second change, then it's moles times the delta H. So here we have 40 grams of water, molar mass of water, that changes it into moles. And then we are given the delta H of fusion, because we were talking about melting, 6.01 kilojoules per mole. So we use that as conversion, and we get 13.3 kilojoules here. Now the last one is again Q equals mc delta T kind of a problem. Okay, it's still 40 grams, but this time we use 4.18, which is the specific heat for liquid water. And then our final temperature, our delta T, we are going from 0 to 25, so it's 25 degrees. And again here, this is going to come out in joules because of our specific heat, so we're going to use a conversion to go from joules to kilojoules. So we have this answer, 4.18 kilojoules. So our final energy for the whole change is to add together all 3 of these values, and we're going to get 17.9 kilojoules of energy. And again, be careful about your units. Okay, this second one, because we're using kilojoules per mole, that naturally comes out in kilojoules. But the other 2, the Q equals mc delta T, because C is usually in joules per gram degree, that answer is going to come out to be joules, so we have to do a conversion to get them to kilojoules before we add them together. Okay, for question 30, how many grams of NO is used up when 428 kilojoules of energy is released? Okay, given here in the problem, we have that 112, so that is really the delta H. It's going to be a conversion, and it says that there's a negative 112 kilojoules every time this reaction goes as written. So we're going to use this negative 112 kilojoules per mole of reaction. So we start off here, the 428 kilojoules of energy is released, negative 428. Here we use our conversion, negative 112 kilojoules per mole of reaction. Now every time this reaction occurs, we're using 2 moles of NO, and then finally we're trying to get grams, so we have to add together an N and an O, and we get 30.01 grams, that's the molar mass. So when we're all done, we find out we have 229 grams of NO is used up when that much heat is released. For part B, if the delta H of NO is positive 34, find the delta H of formation of NO, NO2 and NO. So we're going to go back and do products minus reactants. So we can see what happens. Our products is the 2, I'll change to blue, 2 NO2s, and that's going to be that delta H of formation minus the delta H of formation of 2 NOs and 1 O2. Now remember that O2 is an element, so its delta H of formation is 0. So here we do is we have delta H of the reaction is 2 times the heat of formation of NO2, that's our product, minus 2 times the delta H of formation of the NO and 1 delta H of formation of O2, which is 0 anyway. So we'll put in our numbers. And so the delta H of reaction is negative 112, and that was given in the equation. 2 times 34 and 2 times x plus 0. So now we just solve this little algebra problem, and we find out that the delta H of formation of NO will be positive 90 kilojoules per mole. So you can set this up as an algebra equation. We just have this odd thing here is our x rather than what the delta H is. Okay, the last part is the NO bond energy is 607. The OO bond energy in O2 is 495. Find the bond energy in the NO bond in NO2. So we are still referring to this equation way up here. Okay, but it might be a little bit easier for us to draw all of this stuff out and figure out what's happening. And remember, what's going to happen is we have two NOs and we have an O2. We're going to break those bonds, and we're going to form the bonds in the two NO2s. So I have drawn these out. So you can see what happens is if we have two NOs, that's going to be two NO bonds, and that's going to be 2 times 607 kilojoules. So that'll be a total of energy of 1214 kilojoules. Then we have one OO double bond, which is, we're told in the problem, is 495, so that's going to be 495 kilojoules. But in an NO2 molecule, okay, then it's going to be N between two O's, so we actually have two bonds, two NO bonds, and since there's two molecules, we have 4 NO bonds, and this is what we're looking for. This is our X. So it's going to be 4 times X. Now that would be the energy if we wanted to break those, but we're not breaking them, we're making them, so it's negative X that we are doing. So this is 4X being subtracted. So we're going to put these all together, and we know when we put them all together, this adds up to negative 112 kilojoules, because that was given in the equation. The 112 kilojoules on the right means negative 112 kilojoules. Now let's put that together. So 111214 plus 495 minus 4x is equal to negative 112. That's all kilojoules. Let's solve for x. So let's get x by itself. So we're going to say that 1214 plus 495. I'm going to add 112 to both sides. And I'm going to add 4x to both sides. So it moves my x over here. And all I have to do is divide both sides by 4. And what I get is that x is equal to 457.75, which I'm going to round off to 458 kilojoules. And that's how we do the FRQ problems on the practice test.